And we've seen the following observations. So K is a local field. Standing assumption. And we made the following observations. Closed balls and spheres. Okay, compact. Of course, many times open balls as well. If our field is not a medium. Projective space. The spaces are compact. And it's also so if I have a projective variety, so this is a subvariety, a closed subvariety of projective space, right? So the K points will be a closed set for the K topology. So Vk is compact. Of course, all the compactness statements are respect to the K topology. Strictly speaking, every variety is compact for the Zariski topology, which is not Hausdorff, and it's not very interesting. And the remark is that this is not the last statement, and if and only if statement. So over R, for example, is compact. Also, if I put a plus sign here, it's compact. So now, here's a definition which is not clearly related to the subject. So G here is connected as an algebraic group, solvable algebraic group defined over K. So G is said to be split if, well, as you all know, a group is solvable if and only if it has the composition series such that all the subquotients are big, right? This is a general definition in group theory, also for algebraic groups. A group will be solvable if, of course, you need a decomposition series of algebraic groups. And if G is a K group which is solvable, so I can always find such decomposition series which is defined over K. And the subquotient will be abelian, but I want more. I would say that G is split if it has the composition series defined over K with subquotient, like that, all K isomorphic to the additive group of the field or multiplicative group. And I will give examples. In a minute, this is only one though. Two. So G is split. G is anisomorphic. Oh, by the way, I mean we are dealing with compactness here. But this definition is not only valid. This is an algebraic definition. K could be anything here. G is anisotropic. Again, such a group is anisotropic if it contains no K-split or split. K-split and split are the same. So the notion of splitness depends on K. No split subgroups. And since whenever I have a split subgroup, then in the bottom of the composition series I will find such a thing, then this is the same. G contains no copy of Gn over K, defined over K. And it becomes confusing sometimes with the notion of isotropic group. G is isotropic if it is not anisotropic. It does contain okay, GA or GN. The torus Tn, or if you want, Gm to the n is split. Yeah. So I may think of it as the diagonal group of Tn. The group Un of not strictly, of upper triangular matrices in GLN with ones on the diagonal is split. Let's see this together. So I have this. Sorry?
It contains the subgroup with it contains the subgroup with a single index.
It certainly is isotropic. It contains a subgroup here in the upper left corner, which is a copy of GA. And if I divide by it, maybe let me look at the next step. Now, this corner is also a subgroup. I mean, when I say these corners, I mean, if I fill here things, I leave blank, I leave zeros here, and of course keep the ones here. This is a subgroup, and it contains this one as a center, or as a normal subgroup. And if I divide by this, I'm getting GA squared, and I can divide then by this one. So, and then I can divide by this second guy here, and which is a copy of. Oh, this one is a subgroup. Divided by this is GA, and if I divide, I guess I'm explaining the composition series, or a possible decomposition series for you. And of course, the actual enumeration here can be quite arbitrary. So this is a proof of this fact, and combining these two together, the upper triangular group called Bn sometimes is split. It's called the Borel subgroup of GLN.
So how does it relate to having a split maximum term?
So here I defined. So if a group is a group, you have something in mind. I will relate to that in a minute. But just strictly speaking, a group could be could contain a split maximal torus without being split. As long as this is a definition that is relevant for the class of solo groups. You are familiar with another definition. You define for reductive groups. It's another class. The intersection of these two classes are exactly tori. For reductive group, we will say that it is split if it is contained a split maximal torus. Okay, I'm not there yet.
So it could be that the unipotent radical is not split.
Yeah, well, it could be a priori. It never happens in characteristic zero. I'll come to this in a minute. Okay, we are here. Oh, maybe I'll say. Maybe I'll speak now. So this is an exercise to verify for yourself. In characteristic zero, every connected unipotent group is split. So I'll remind you what a unipotent group is. A group is unipotent, and the element is unipotent if all its eigenvalues for any linear representation of it or of the group containing it, all the eigenvalues are ones. So this definition of the unipotent element. A group is unipotent if all its elements are unipotent, and we know that every unipotent group over an algebraically closed field can be always diagonalizable. Triangulizable. Right? This is Lee Colvin. And so obviously unipotent groups, I mean the splitness theory means nothing basically over algebraically closed fields. It's about the relation between K and its algebraic closure somehow. So if I have a connected unipotent group, I can put it inside UN, say, and then I can use the decomposition series of UN itself, and and I can prove it by induction that it is split. Each subquotient will be contained in the subquotients of this one, which are one-dimensional. It will be a certain subgroup of GA, right? What kind of subgroup of GA could it be? I mean, either one-dimensional, which means the whole thing, or zero-dimensional, or algebraic subgroup, it's not arbitrary subgroup, which means finite. In characteristic zero, the additive group of the field does not have any finite non-trivial subgroup. Done, right? In characteristic P, it doesn't hold anymore. Okay. Maybe an analogy for this every, now non-characteristic assumption, every connected K subgroup K subgroup or every connected terms every connected K subgroup of the talks Tn is split. So again, this is an exercise. Take Tn. There is a standard decomposition series here coming from the embedding of Gn to the K inside Gn to the n, coming from the first K coordinates, the n coordinate thing. And so this is the decomposition series. The subquotients will be one-dimensional. This is the proof that this is split, right? When I'm taking an arbitrary subgroup, the subquotient might not be one-dimensional anymore. I mean, they're either zero-dimensional or one-dimensional in each case. If one-dimensional, fine. If zero-dimensional, they need not be trivial anymore. The K star does have finite subgroups, right? But only groups of roots of unity of a certain order. This is the only one. And then if I divide Gm by mu k, roots of unity of I mean, I'm having the map Gn to Gm, x goes to x to the k. This is the kernel. So I can identify this with Gn again. Right? So this shows that, I mean, use this to solve this exercise. In any case, this is classical and described in any decent course in algebraic groups. This fact, you have it in Borel's book, for example, just to remind ourselves, the category of tori, if we consider algebraic groups, and we look at tori, there is a equivalence of categories with the categories of Z modules, finite generated Z modules. The functor carries one to another is the functor of characters. Characters on a torus is an abelian. It's like Pontryagin do thing, right? Which is valid in this category. Okay, let me move on. So combining these two together, if we assume characteristic 0, every connected K subgroup, probably I'm forgetting occasionally the K sign here, K subgroup of Bn is split. Again, this is not one characteristic 0, so we have this this parenthesis in our discussion on compactness, but maybe I'll tell you the secret. There is a relation between anisotropicity and compactness. It's the same thing of all of things, somehow. But let me still discuss examples. Maybe I already give you a hint for the following. Can you give me an anisotropic torus over the rays? So you know, a torus over one-dimensional torus over the rays is, for example, is R star, right? I mean, it's the group is, if you wish, C star is GM, because the multiplicative group of the field. R star, when I say R star, regarding R, I'm doing some illegal move here. I'm thinking of the R points of a certain real structure on that group. there is another real structure on the same group, and for which we will get different set of real points. So what I'm asking you to be precise is what will be the other set of real points.
The circle.
Hmm?
The circle.
The circle, or SO2. SO2 is an anisotropic. SO2, anisotropic torus over the rings. If you want, SO2 is a real group, is a real algebraic group. I can regard the complex point of it over the complex numbers by this description of it. Here we preserve a 1-1 form, the standard inner product on C2 or R2. That's where we're looking. Over C, this inner product is the same as the 1-1 inner product, right? I mean, that inner product or that quadratic form is equivalent over the real numbers with that quadratic form over the complex numbers, right? If I can change the coordinates y to iy. And so over the complex number, it's the same as SO11, which I guess you should know. This is the same as K star. This is the multiplicative group. By over the rings, I can write it explicitly in coordinates by using this one. I write using a trigonometric function, right? Cosinus theta, sinus theta, minus sinus theta, cosinus theta. And I would use quadratic trigonometric functions in order to describe this one. Probably. In any case, so this is one example. And again, I guess if I'm leaving, if you, for those of you who see such things for the first time, I'm leaving many details here to observe by yourselves. Now, but I wanted to say something else. Here is a related example. Take C star. So actually, this is something. So as a real group, this is the same as this one. So this is a product of two tori. One of them is split, and one of them is anisotropic. So this is an isotropic group. Which is neither anisotropic nor split. Of course. But this is not an arbitrary example. I choose it for a reason. So actually, I took the multiplicative group of the complex number, and I choose to view it as a real group. Okay, what I did here is I did a restrictions of scalars thing. So, which we did before many times, but in particular, I think when we discussed analytic functions, we discussed that every complex, we discussed the Cauchy-Riemann equation. The Cauchy-Riemann equation is a polynomial equation on GL2R, which actually specifies the subgroup C star in it. So this it specifies an embedding of C star into GL2R. This is exactly what. When I regard C star as a subgroup of GL2R in this way, having the Cauchy-Riemann equation as my defining polynomial, I'm getting the real structure on that one. So what is the Cauchy-Riemann equation? It's the equation that guaranteed the commutation with I, right? I mean, a real linear map of a complex vector space seen as a real vector space. In this case, the complex vector space is just the one-dimensional line, C. I'm taking a real linear transformation of that, GL2R, and I'm requiring further that I will commute with I, then I will commute with any complex scalar, and I will respect the C linear structure. So I will be in GL1C, right? So this is a typical example, and I want to give the following illustration of the same phenomenon before writing it in a more general form. And again, writing this down, first at least, I will not be super formal. I'm writing down points over the field. So think about over FP. And think about maybe GL2FP. So here we have the standard torus of diagonal matrices. How many points do we have in this torus? How many FP points?
P minus 1 square.
P minus 1 square. But now I'm going to give you another torus. It will have another set of points. And I will leave it to you to see that this is a torus. So I can identify FP squared. This is a invertible linear transformations of FP squared. I can identify FP square with FP squared. Right? So I'm writing here under the identification. FP square, just by choosing coordinates, I can identify these two as a vector space over choosing coordinates here. I mean, one maybe, and another element which is not in FP. I'm taking as a basis. This gives me such an identification. And FP square star will act on this guy. So this gives me, and of course it will respect the FP structure. Actually, it will respect the one-dimensional FP square linear structure. I'm talking here about GL1 FP square. And I have the natural embedding here. Right? So how many points do I have here? You know, P square minus 1. It's not the same. So this is another torus. Maybe I will not write it down, just I will say it aloud. I mean, formally what I'm writing here is just on the level of FP points. I'm writing something. But I'm having in mind this as an actual algebraic group defined over FP. Right? As the same way I was asking you to think here. Think about FP square. And the guys in GL2 FP that respect the one-dimensional FP square linear structure are exactly those which commute with multiplication by those elements. So choosing this identification, each element of that guy I can write down as a matrix in coordinates. This is not yet my group. My group will actually be the commutant of that one. I want to commute with those matrices. So I will have finitely many polynomial conditions for that. This will define for me some subgroup of this one, which will be exactly this one on the level of FP points. Right? But what I described now is a way to think of this not as a finite group of order P square minus 1, but as a group defined by polynomial. So it makes sense to define these over FP bar, for example. Okay? So again, those things I don't want to write down on the board, but I want you to understand this, and maybe in PGLM, the image will be the image of the group G that I'm describing like that here. Now I will take the FP points will be FP squared minus F. I should divide by the actual scalar matrices coming from FP squared. Its size is P plus 1. So this is an anisotropic torus. You should think of this as a you should think of this as a compact group somehow. It's like you may think about this as a projective line in some way, and this is a circle. I mean, this is the same as SO2. I divided by this factor here, right? I divided by this one, which is an analog of that one. So this is the way I could see this coming from somehow this anisotropic torus is related to the fact that I have for the rings I have a field extension of order 2. So this is why I do have such a torus. And actually, as you may know, for the rings, I have only those kind of torus, one-dimensional torus. Every torus over the rings is a product of such guys with such guys. You know it when you try to diagonalize things over the rings. You get 2 by 2 blocks or 1 by 1 blocks, right? This is, you are familiar with this phenomena. So somehow it is related, as you probably noticed in this way or another, to the fact that R is of order 2 inside C, of index 2. And of course, over FP, I can do it for higher. I can take K here instead of 2, and I can define this way other anisotropic tori. And actually, this is the way that all anisotropic tori get born, coming from field extensions this way. And I mean, this is not the subject of this lecture now, but this is something that we should know.
PGL2 is a projective variety, right?
No, it's an affine variety. Every affine group is an affine variety. Yes, it is. This is something that, it's confused people for that if you see it the first time. Of course, you can define it as a subset of P and N, right? If you have GLN, this is an open subset of Mn, I can projectivize this vector space to have this projective space. This is open here. So this is open here, it is not closed. Of course, every affine space could be put as an open subset of a projective variety, but never, unless finite, never as a closed subspace.
Yeah, that's what I'm doing.
Yeah, so PGL2 always is affine. This is a fact. Actually, we know that every algebraic group, whenever you have every algebraic group that you get, for example, if you take a given algebraic group, which is by definition a affine variety, and you divide by a normal subgroup, there is always an affine structure on that one. I mean, when I say algebraic group, I mean affine algebraic group, linear algebraic group. There is another class called, for example, called the Billian varieties, which are projective. I don't touch those here, not in this class. And but the thing is that the class of affine variety is closed under the standard operation. So, for example, take quotient by normal subgroup. Maybe, so I said enough about this. Just I'll write this cryptic slogan, generalize for finite field extension. So if you have, let's say, if I have a small field K, I have a finite field extension of it. F, I can look at F star. This always will be a torus over F. But now I will restrict the scalars to K. And I will regard this as a K group. Okay, I will put a K structure on this group. It will not be one-dimensional group anymore. The dimension of this group will be the degree of the extension, F over K. Okay, I don't know, maybe I will come back to the abstract notion of restriction of scalars, which is very important, but I think we all have a feeling of what it is, even though I didn't define it formally here. Probably most of you have seen this in the past, the formal definition, but more or less I did say it. Actually, I didn't need to take a field here. I could take a division algebra of finite degree over a certain field, and then I will get D star. If this is division algebra, D star will be a group, which can be defined, could be thought of as a group over K, and I can give a K structure to it. And then this will not be commutative anymore. It will not be solvable in most cases. But I will get very interesting examples of algebraic groups. If after taking some finite extension, finite field extension, D will be split, and this will be just GLN, right? But okay. Oh, GLN in case K was central. I mean, okay. K was the center of D. Okay, then it has something you know very well from Bauer theory. What is it? I want to say more. Maybe again, without going into the details, just something for you to think of if you're bored. Something happens is happening if my field is not perfect, and if I have characteristic P, and the field extension degree will be the same as the characteristic. So I'll just write this as a final example. You can explore further why it is so funny. I'll take FP, take the P root of P as N F P. So I'm doing more or less the same thing that I did so far, but if I took this specific example, what is funny here is that when I will divide by FPT star. You should convince yourself that I will get a P group. Every element will be of order P. This is kind of clear, right? I'm multiplicative. So if I'm taking a group here and I'm taking a P power, I'm taking an element here, I'm taking a P power, I'm getting inside this, right? So dividing by FPT star, every element to the P power is the identity. So the thing that I will get performing this move here will not be a torus anymore. It will be unipotent. Okay? But this group here does not have any unipotent subgroup. Because any unique subgroup is a P group. and I don't have any element of order P here. Every element here is of finite order, of infinite order. So this is a bizarre thing that could happen in positive characteristic, and we should be aware of that. And again, it's just a warning sign, and I'm not going into this corner. I just want you to know this. Okay. And here's the theorem. So this is a fixed point theorem. And this is the theorem that actually relates the notion of splitness and our notion of compactness. So now I'm going back to think of a lot of things. G split solvable. And I'm having an action on some K variety. So this is a K action. And I'm looking at the K points in V, and assume I'm having some subset. Now I want to think about it as a topological space. Forget algebra. Right? Maybe this is a real variety here, or periodic. So I'm having X. What I'm asking X to be is assume X is compact subset and G invariant. Then there exists a GK field point. X. Okay, the proof is rather easy, but maybe I will need it after the break. Let me give it more right now. So that's easy one. Assume G is connected. Very good. G is split solvable if and only if. So this is a standing assumption, and now I'm having this if and only if. G is triangulizable in each K representation. So whenever I let G act linearly on a vector space, I can triangulize it if and only if G is triangulizable for some injective K representation. Now, I claim that first of all, I claim this is a complete triviality, and I claim that this we know as well. I think this is that, right? So I just have to prove this one for you.
The flag, right?
Hmm?
The flag, right?
Yes, so I will take here, so assume G is splits-over. So it's a K group which is connected and splits over, so it fits into the assumption of this thing. And assume I'm having any linear representation, I'm trying to prove now this piece. So assuming I'm having any linear representation, I'm looking now on the space of flags of that vector space. Of course, a group is linearizable, is triangulizable, if and only if it fixes a separate flag, right? So this will be my V. X will be all Vk. Okay? And there will be a fixed point there. There will be a point fixed by Gk, which so it will be a point defined over K, a K flag. So my group is K diagonalizable.
What about the compact part?
No, so Vk itself is compact. X will be everything. This is okay. I had this. This is a projective variety, hence compact. I'm over a local field. So by this I prove that one, and I have a full circle, right? But this works only. I mean, this is not true over a positive characteristic. So the next thing I should do is to prove the theorem for you. So maybe I will say now I'll spell out a proof, which is not the proof I will write on the board, but it is. I will just say it is very easy, and later on I will write a more pedantic proof on the board. But I want. Well, here's a language that we are not using yet, but at some point I will get to use. So the language of ergodic theory, which makes such theorems very, very easy. So what I want to say, what I want to notice is that by the splitness comes about because by reducing this theorem to the one-dimensional groups GA and GM, right? If I know how to prove it for G being GA, then it is easy to deduce it in or GA or GM, then it is easy to deduce it in general, right? Because I'm taking the first guy in the decomposition series of G, the first actual subgroup, it acts on X, it has a fixed point, assuming I did that case. And then on that, on the space of point fixed by this guy, which is non-empty, this will be my new X. The quotient group acts. And I get the result by induction. Okay, this is a standard trick. So I need only to do it for GA and GK, and GM. Or of K and K star. So the thing is that because X is compact, and again, I will give another proof of another flavor later, but because X is compact and because G is solvable and it's abelian, I have an invariant measure. I have G invariant measure somewhat. And actually I can take a G invariant ergodic measure, which I always have by ergodic decomposition. And because the orbits are locally closed, such an invariant measure, ergodic measure, will be supported only on one orbit. One orbit of my group, which is now either K or K star, right? So this orbit will be either one-dimensional orbit or zero-dimensional orbit. So it will be my group divided by something zero-dimensional or divided by something one-dimensional. If it is a one-dimensional, or if it is zero-dimensional orbit, because the group is connected to begin with, it's just a point and I'm done. If it is one-dimensional orbit, so my invariant measure is on this quotient, one-dimensional quotient of my one-dimensional abelian group. So I'm having here a one-dimensional abelian group, which is not compact. It was a non-compact group divided by finite group. I divided by the stabilizer, which is zero-dimensional. So I'm having a non-compact group, locally compact group, that supports an invariant probability measure, which I cannot have. I don't know, this part of the general notion of locally compact groups. A group has an invariant probability measure, the Haar measure is invariant if and only if it is compact. By this I get a contradiction, and I'm done. Okay? So again, in 2 hours from now,
In an hour from now, I will prove this in a more traditional algebraic way, but the proof that I just spelled out is useful, and we will use it in the future.